In this video, we will work with spectrometers, serial dilutions, calculating absorbance and concentration, as well as understanding the graphs and data tables presented to us. Below, you will see our blank solution, which is used to clear or zero out the spectrometer. Seeing this, I will have an arrow that points exactly where the meniscus is where you should fill it to the cuvette. Anything over this can result in spilling in the spectrometer, as well as an inaccurate read. Starting off with our first blank solution, we will place it in the spectrometer with arrows to the sides. Also making sure it was clean. As you can see, you're wiping it off, shutting the spectrometer, and then zeroing out on the computer. Once we zero out, we can then start running our other solutions, including our stock, into the computer. This is very important. While we are going ahead and recording our blank, a few things I wanted to point out is that we do use the wavelength scanning to determine the absorbance and concentration of an average of all of our scans ran by each dilution. What we will do is add all of our dilutions up, get the average, and then that'll kind of tell us our absorbance and our concentration when we do later calculations in the video. Moving on to our next thing that you should know about is the lambda max. This is the wavelength at which a substance has its strongest photon absorption, basically the highest point along the spectrum's y-axis if you look at it in other terms. The lambda max refers to the wavelength along the absorption spectrum where a substance has its strongest photon absorption, and therefore it can kind of tell us the parameter to compare the different qualities of the molecules within substances. As you can see in this next clip, we are just finishing up writing down those last couple averages of those trials. We typically do 2 to 3 trials per solution. And what we're doing here is we're just kind of flipping over to our graph to look at the peak and seeing the results that we're getting in the nanometers of the reading for that. So what we're doing next is we're getting ready to put our stock solution in here, which you will see next. It's a kind of a dark blue solution, but then we will run that about 3 times and get the average for it, and then repeat for the same or the following dilutions. And as you can also see, again here, making sure that we clean it really good. We open the spectrometer lid, put it in very delicately, which can be kind of confusing to find those little arrows, but once we get it in there, it's pretty good to go. So we're just going to slide it in there, make sure it's secure, and then pull the lid down. And then again, we are going to get ready to run our 2 to 3 trials and then calculate that average. And getting to our final dilution, as you can see, we're just finishing up here at the top where that little arrow is. That is our 3 scans that we ran. So again, we'll take all those in and get that average and then start the calculations. Okay, so moving on to calculations, if I haven't mentioned this earlier, the Beer-Lambert law, which is A equals ELC. A is absorbance, E is the molar extinction coefficient, L is the length of path light it must travel in the solution in centimeters, and C is the concentration of a given solution. We then measured out 0.124 grams of copper sulfate pentahydrate, then divided that by the molar mass to get our moles. Once we got our moles, we then divided the moles by the liters to get the molarity of the stock solution, which is 0.025 liters. From then, the molarity we used the M1V1 equals M2V2 equation, and then used that along with the molarity of the stock solutions to get the molarity of the dilutions. After then arranging those numbers and getting what we need, we pretty much manipulated and arranged the formula A equals ELC, otherwise known as Beer-Lambert's law, to find the concentration, and then plugged our values into the formula, which gave us our variables. We then rearranged the formula A equals ELC, otherwise known as Lambert's law, to find the concentration, and plugged in our found values into the formula to give us our variables. If absorbance increases, concentration should increase, is what we found, proven in the chart.